We're going to work through a few examples of implicit differentiation to help show how it works. So first example, x squared plus y squared equals 25. And the example is asking us to find the derivative, find dy by dx. So I'm going to take the derivative of both sides. So d by dx of x squared plus y squared is equal to d by dx of 25. And as you get practice, you won't necessarily need to write all this out. I'm going to write it out on this first example so that you can really hopefully see what I'm doing. So the derivative of x squared plus y squared, that's going to be the same as the derivative of x squared plus the derivative of y squared. The derivative of 25 as a constant is equal to 0. Derivative of x squared, that one's nice and easy, it's 2x. The derivative of y squared, remember that y is not x. Y is a function of x. So this is actually a composite function. It's the composite function of y equals f of x. So it's f of x squared. Now we don't know what f of x is, we just know that it presumably exists. So we need to use the chain rule here. We're going to get 2 times y, because we're going to evaluate the outer part first. 2 times y to the first. Then I'm going to multiply by the derivative of y, which we know to be y prime. So this is where that y prime stuff comes up. Let me write that as a 1 just so it's a little bit clearer. So 2 times y to the first times y prime. So now I need to isolate my y prime on one side. So I'm going to leave it here, and I'm going to have 2y y prime is equal to negative 2x. Then I'm going to divide by everything that's not y prime. So I'm going to get negative 2x over 2y, which means that the derivative of y is negative x over y. So you'll notice here that this means that the slope depends not only on x but on y, and that's because this function here, when you isolate y, you actually end up getting two functions. You get y equals plus minus square root of 25 minus x squared. So there's actually two values, which means we need to figure out which of those to correspond to the slope. But you'll see that the derivative does have that y dependence. All right, as a second example, x cubed sine of y plus y equals 4x plus 3. I'm going to do this one with a little less detail, but I'll still talk through everything that we do on both sides. So first, I'm going to take the derivative of both sides. The right side is easier, so let's just knock that out first. That's going to be 4 plus 0, so it's just 4. I'll write the plus 0 so you can see that I did deal with it. Now, on the left side, I have two functions multiplied by each other, so I need to use the product rule. So the product rule is find the derivative of the first one, 3x squared, times the second term, so times sine of y, plus the derivative of the second term, cosine of y, times the first term, x cubed. So I'm going to put that in brackets just so that we can link those, and it might be easier to track where things came from when you're looking back. And then plus the derivative of y, as we've said before, that's derivative of y prime. And I missed the derivative of sine of y should be cosine of y, y prime. Because again, this y is assumed or implied to be a function. So sine of y is actually a composite function, so I need to use the chain rule. So I do the outer part, cosine of y, times the derivative of the inner part, y prime. Now, I'm going to isolate y prime by leaving everything that has a y prime on the left side. Put the x cubed out front just so it's easier to work with. Y prime plus y prime is equal to 4 minus 3x squared times sine of y. Factor out y prime, and I'll get x cubed times cosine of y plus 1 is equal to 4 minus 3x squared sine of x. And if I divide, I will have y prime is equal to 4 minus 3x squared sine of x over x cubed cosine of y plus 1. And that is our derivative. Now you'll note, the algebra isn't the cleanest, it doesn't look the prettiest, but by definition, when you're doing implicit differentiation, because of the way that it works, your y primes will only ever come from the chain rule, which means you'll only ever have first order, or y prime to the first, which means you'll always be able to do this algebra step. There might be a lot of nasty, ugly stuff that you factored y prime away from, but it will factor just one away and leave you with a bunch of stuff that doesn't have y prime. Likewise, there might be a bunch of nasty, ugly stuff on the right or on the other side. So you might have a really ugly fraction, but it should be an easy fraction to come up with. It might have a lot of terms, but it should be easy to come up with. If you ever end up with a y prime squared, you know that you've made a mistake, or cubed, or divided by y prime, or anything like that. You should never end up with something along those lines. All right, let's take a look at our last example here, which has a little bit more going on in terms of things being multiplied together. But again, it is fairly straightforward once we kind of just start plugging through. So let's do the derivative of the right side first, because that's a little bit simpler. It's a composite function of y, and then that function squared. So the derivative is going to be 2 times y to the first times the derivative of y, which is y prime. The right side, the 3x, is easy to derive. It's just 3. This x squared, xy squared, is a little bit trickier to deal with. There's a couple ways to do it. First, we can distribute the squared and do x squared times y squared. In fact, I think I will do it that way, but if you preferred, you could do the chain rule and do 2 times xy times the derivative of xy. But I'm going to distribute, and we're going to get the derivative of x squared y squared, just because that's going to be a little bit easier, I think, to work out. So the derivative of x squared y squared is going to be the derivative of x squared, which is 2x times y squared, plus the derivative of y squared, which is 2y y prime, because of the chain rule, times x squared plus 3 is equal to 2y times y prime. Now you move everything with y prime to one side, everything without y prime to the other. So I'll leave the non-y prime stuff on the left here, just because then I'll have fewer negatives. Plus 3 is equal to 2y y prime minus 2y y prime x squared. I'm going to factor out y prime from the right and then divide everything that's left over. So I get 2x y squared plus 3 over 2y minus 2yx squared is equal to y prime. 2y minus 2yx squared, the leftover thing is y prime, and that will be our derivative. So if you're happy with those examples, you can wrap up here. I will show deriving the other way here, just as a quick example if you want to see it, and you'll see we get the same result. So as an addendum here, we're going to do 2 times xy times the derivative of that inner function xy. So 2 times xy is going to be multiplied by x times y prime plus x prime, which is 1, times y prime. And if I distribute that, I get 2x squared y prime plus 2xy. Sorry, this should not be derived because it should be the power rule, so 2yy. So 2x squared y prime plus 2xy squared, which you see are the same as those two there. All right, that will wrap up our implicit differentiation examples.